define what we mean by a metric space. Definition. The pair X, D. This pair contains the non-empty set X and a metric D defined on it. So the pair D is called a metric space. So that's what we mean by a metric space. We take some examples, e.g. we start from the very simple ones we know about, and then we graduate to more interesting examples. Let X be the set of real numbers. And we define D, so we define D on X cross X into R by D of X, Y is equal to the absolute value of X minus Y. So this function defined this way, then D is a metric on X. We call this the usual metric on the set of real numbers. So throughout the discussions we are going to have on this course, if I mention the set of real numbers and I do not specify a metric, then understanding that the metric we're using is this one, the absolute value. Okay. First, we need to justify that this satisfies axioms 1, 2, and 3 in the definition. So we can now confidently call this a metric on the set X. Before we verify that D is a metric, first notice that this function is well defined. That is D of X, Y equals absolute value of X minus Y is a well defined function because you can see that for any two elements in the domain of this function, they do not share the same image. And of course, for any element you take in the domain, the image is in the set R. So this function is well defined. Next, for condition number 1, that's A1, we know that for all X and Y in the set capital X, where these are X is the set of real numbers, it is true that absolute value of X minus Y is bigger than or equal to 0. From the definition of absolute value function, we know this is true. Next, we also know that absolute value of X minus Y is equal to 0 if and only if X minus Y is equal to 0. And this is true if and only if X is equal to 1. So what we have done is that we've shown that D of X, Y is bigger than or equal to 0. We also have shown that D of X, Y is 0 if and only if X is equal to 1. So this is done. For condition number 2, it is also not difficult to see. For any X and any Y, we take arbitrary from capital X, D of X, Y is equal to the absolute value of X minus Y. But this is the same as the absolute value of minus Y minus X. Again, by property of absolute value function, this is the same as the absolute value of minus 1 multiplied by the absolute value of X minus Y. So what we have done is we've shown that D X, Y, which is the same as X minus Y, is the same as absolute value of minus 1 multiplied by absolute value of Y minus X. But absolute value of minus 1 is 1. You multiply this by this, you get itself. So this is the same as absolute value of Y minus X. According to the definition of D, this is nothing but D of Y, X. So what we've gotten is D X, Y is the same as D of Y, X. Verifying the symmetric conjunction. So this function satisfies the symmetric condition. Alright. For condition number 3, let's just take x, y, z in capital X arbitrary. V of x comma y by definition is the same as x minus y. This is the same as absolute value of x minus z plus z minus y. Because minus z plus z is 0, so we are back to where we came from. Again, using triangle inequality that is valid for the absolute value function, we have that this is less than or equal to absolute value of x minus y plus absolute value of z minus y. By definition, this is d of x comma z plus d of z comma y. Therefore, this function also satisfies the triangle inequality. Because D satisfies those three conditions, we can conclusion, D is a metric on